So let's begin today's discussion by considering a problem. And the problem goes something like this. Imagine that you were a lifeguard at a beach and that you spot a potential drowning victim in the water. That's me, the drowning victim, your physics professor. And your goal, of course, is to save me. So considering that you can run on the beach faster than you can swim, okay, what path should you take to reach the victim, me, in the least amount of time? Well, you see me, now you see you. There you are. Now, certainly the straight line path represented by this blue arrow would represent the path of least distance. But that may not be the path of least time, considering the fact that you can run on the sand faster than you can swim in the water. Well, if we consider this path here is certainly not the path of least distance, but this would allow you to spend the least amount of time in the water. But which path should you actually take to reach me in the least amount of time? Well, that path, of course, will depend upon how much faster you can run on the sand than you can swim in the water. Okay, so like we're saying here, the straight line path representing the path of least distance would not be the path of least time. Okay, you would be able to arrive at your victim faster when you spend more time on the sand, okay, where you can actually travel faster. So the amount of bending at the shoreline really depends, of course, on how much faster you can run than you can swim. So the actual path of least time is probably going to represent a balance between the green path I'm showing you here and the blue path. And of course, the actual path is going to depend upon, okay, your speed in the sand as well as your speed in the water. Now, if you're asking yourself, what does this have anything to do with light? Well, consider what we know about Fermat's principle of least time. Okay, light behaves very much in the same way as a lifeguard does. Light will take the path of least time, not necessarily the path of least distance. So we'll begin our discussion of refraction today from a qualitative point of view, and then as our discussion progresses, we'll become a little more quantitative in our description of refraction. So before we actually define what refraction is, let's review a little bit about wave theory, and this is nothing new. This is something we said last time as well. Okay, the rules for the reflection and transmission of waves at boundaries. So when a wave is traveling in one medium and it enters a new medium, we can say that at the boundary between the media, some of that wave's energy will get reflected into the initial medium, some of the wave's energy will get transmitted into the new medium. What determines how much of that wave's energy gets reflected versus transmitted at the boundary? That depends upon the difference in the wave speed, okay, at that boundary, the difference in wave speed between the two media. And remember, we said that the wave speed, okay, depends upon these two factors. The elasticity of the medium, right? The speed of the wave is directly proportional to this elastic factor and is inversely proportional to this inertial factor, which is typically measured by the density of the media. So, last time we looked at, okay, and you see here in the simulation that when the wave comes in, we see that, and it encounters the boundary, we see that some of that energy gets reflected here. So we have a reflected wave. That's what we talked about last time, okay? But this time we're going to now focus upon what happens to the transmitted wave. Okay, so last lesson we looked at the reflected wave. In today's lesson we'll be focusing exclusively on that transmitted wave. And let's now define this concept of refraction. Refraction can be thought of as, okay, this phenomenon where the wave direction changes, okay, as the wave enters a new medium at some angle with respect to the normal. So all I'm saying here is that if the wave was to enter the medium right along the normal line, for that one special case where you have an incident angle of 0 degrees, then you would have no refraction. You would get no bending of the light when it enters a new medium. For all other angles, you will find, as you see in this simulation here, that that light ray is going to bend as it enters a new medium.
So what would actually cause light waves to actually bend when they entered a new medium? Well, if we want to try to explain this macroscopically, we can say very simply that the cause of the refraction, the cause of the bending, is due to the fact that the waves change speed as they go from one medium into another. And it's this change in wave speed that causes the direction of the ray, the direction of the wave to change, okay, as it enters a new medium. Microscopically speaking, if we want to try to explain, what is it that causes the speed to change? Well, when light travels through a transparent medium, okay, like glass, for example, that energy must be absorbed and then re-emitted by the atoms in that medium. And this absorption and subsequent re-emission, this process takes time and ultimately slows down, okay, the speed of light. So the greater the delay between absorption and re-emission of that energy, okay, the slower the light wave is going to travel in that particular media. So if you want to try to explain why the refraction happens at the boundary, there's a very good analogy that I think really nicely helps explain the bending that occurs. And the analogy I'm going to use is, consider what would happen if your car, if we look at the axle of your car as you're traveling from one medium into another. And I'm going to say from concrete into mud, because I think that we all have experience of how our car moves in concrete and how it moves in mud. We know that our tires are going to move much faster in concrete than they are in mud. So let's take a look at a picture here. Here's the concrete and here's the mud. And here I'm showing you the front axle of your car. Now, when your car is entirely in concrete, then it's reasonable to assume that your right wheel would travel exactly the same distance as your left wheel would, okay, if both wheels are traveling on the same type of surface. In which case, okay, when your front axle is traveling entirely in this first medium of concrete and both wheels travel the same distance in the same time, okay, well, you could infer that your car and axle would be traveling in a straight line. So you'll notice what I'm showing you here in this picture is really the position of the front axle of your car at given intervals of time, let's say at 1 second time intervals. Now let's consider what happens when your right-hand tire hits the boundary between the concrete and mud. Notice that your right-hand tire is going to hit the mud before the left-hand tire. Okay, and the truth is we only get refraction of light waves when that light ray or wave enters the medium at an angle as the car is entering the medium at an angle. If we think about it, in the next interval of time, okay, your right-hand tire, which is traveling in mud, is not going to be able to travel as far as your left-hand tire, which has been traveling in the concrete. The end result is that this is going to cause your front axle to bend. Okay, your car is going to change directions. Now, from here on out, okay, you'll notice that all of your tires, that is the right and left tire, are now both in mud, so they will both travel the same distance in the same amount of time. So once both wheels are in mud, your car will once again travel in a straight line. Notice that the bending or the refraction happens exclusively at the boundary between the media. So while this is true for front axles of cars changing media, it's also true for light waves when they enter a new medium. Notice that in the picture on the left, your front axle is able to travel a greater distance in a 1 second time interval, right? The distance between these axle shots is bigger than when your car is traveling in the mud, and both wheels can travel a smaller distance in a given time because they're traveling slower. So I think this picture nicely illustrates what's happening when a light wave enters a medium at an angle, it enters a new medium at an angle with respect to the boundary, okay, and why you actually get this bending to occur upon entry.
So in this slide, we will state the rules of bending. In other words, okay, state the rule that determines which way light is going to bend as it enters the new medium. And to give us a little help here, we recruit our friendly one-eared rabbit Bongo, and we'll always take advice from a one-eared rabbit when he says, learn the rules of bending, but don't bend the rules. So very good advice, Bongo. Let's see what you mean by that. Here I'm showing you two different slabs here, okay, and the normal to the interface between those two slabs. So we're assuming that light will travel faster in one media than it will in the other. So when a light wave enters a material where it speeds up, the rule says that it gets bent away from the normal. And if I show you an incident ray here traveling in this medium, perhaps because this is a more optically dense medium, and this purple ray gets refracted when it gets bent at the boundary between the new media. So it's entering a medium where the optical density is probably lower and it can actually speed up. When that light wave speeds up, it gets bent away from the normal. Okay, conversely, when you have a light wave which enters a medium where it slows down, so if we have a light ray going exactly in the opposite from this medium here represented in the red ray, okay, into the medium where it slows down, in that case it would make sense that the ray would get bent towards the normal. So let's actually, rather than just look at this through a simulation, if seeing is believing, in the next slide, okay, we'll take a look at this in real time where you'll actually see the real refraction of light, okay, traveling through a transparent media.
All right, so folks, let's take a look at some refraction of light in real time. As you'll see in this setup, we have a laser which is shining a beam of light through air when that beam actually hits a piece of plastic right here, or perspex. And you'll see that when the light enters the new medium, when it enters the plastic, you'll see how it gets bent towards the normal. When we look at the incoming light here, we see that there's an incident angle with respect to the normal, which with our protractor back there, we can make a reading for, and it turns out it's about 60 degrees. But because of the refraction of light, when we actually measure that angle of refraction right here, we see that the angle of refraction is only about half of that, about 30 degrees. So clearly we see that when light enters a medium where it slows down, that is when it goes from a less optically dense medium into a more optically dense medium, the light ray gets bent towards the normal. In the next several slides, we'll take a look at some of the effects of refraction. And I should point out that when it comes to optical illusions, what we a lot of times would see in a magic show, that the optical illusions we often see involve nothing more than refraction, the bending of light that can very often fool the mind. So in the next slide, we'll take a look at what I call the disappearing coin trick, okay, which is nothing more than an optical illusion involving some refraction. All right, folks, this magic trick. All right, folks, this magic trick I'm about to show you makes use of the refraction of light. What you're looking at here, you can see this styrofoam cup, but you can't see the coin right now. But what I'm going to do is I'm going to tip it towards you so you can see there's a coin down there in the bottom of the cup. But when I put the cup in this position, that coin is just slightly outside of your view. But notice what happens when I slowly add water to the cup. Okay, as I slowly add water into this cup, you should see that coin start to come into your view. Okay, and as we will explain, this is all due to the fact that light is getting refracted or bent at the surface of the water. All right, so let's try to explain what made that coin magically reappear when water was added to the cup. So you'll notice over here in the cup on the left-hand portion of your screen here that this cup is full of air, no water. And when we look at an example of a light ray that leaves the very far side of that coin, that light ray, which is traveling exclusively through air and barely misses the side of the cup, that light ray barely misses your eye, which makes that part of the coin undetectable to your eye. Notice what happens when we look at the cup on the right, which is now filled with water. If I take a look at even a ray that has an angle of incidence like this, when that ray is traveling from water and then hits the boundary between air, remember the light ray is traveling from a more optically dense medium into a less optically dense medium where it speeds up. That tells us that that light ray bends away from the normal and can now enter your eye. So for this particular light ray and for many other light rays, that leave the coin, you will be able to see the coin. So because of the refraction of the light at the boundary or the interface between the water and air, that bending away from the normal now allows the light leaving the coin to be detected by your eye. So this magic effect is nothing more than the refraction of light. So stay tuned for my next demonstration, which is what I call thumb on steroids, where you're going to see me add my thumb to a graduated cylinder, and get it to magically grow. All right, everyone. This refraction demo is what I like to call thumb on steroids. And let me tell you what I'm going to do before we do it. But you're going to take a look at my thumb inside of this beaker, this beaker full of air, and you're going to see an image of my thumb because light is going to get reflected off my thumb and into your eye. Then I'm going to take some of this special solution here. This is called digit enlargement solution. And it's going to replace the air that's in the beaker. And you're going to see what happens to my thumb. So let's start by taking a look at my thumb in air. I think everybody can see an image of it. Let's now take some of this special digit enlargement solution. Pour it in here. And let's see what happens when I stick my thumb in. Oh my gosh. Can you see that? Looks like my thumb grew in size. What am I going to do to get it out of this beaker? Now I know what many of you are thinking to yourselves right now, and that is, hey, why doesn't this guy give up his day job and become a professional magician? Well, that thought has crossed my mind, but don't worry, it absolutely will not happen before the end of this course. So let's try to explain the physics, or maybe I should say magic, behind the thumb on steroids. So I realize that I did this with a graduated cylinder, but it works equally well with test tubes. So what I'm showing you here is my eye. I'm showing you the graduated cylinder, in this case test tube filled with water, and here is my thumb inside of the test tube. Don't actually ask me how it got in that way. Maybe it was cut off at some point. Okay, at any rate, when you let's take a look at one little part of my thumb, one little piece of my thumb right here. And if we look at a light ray that leaves that point on my thumb, when that light ray travels through the water and hits the boundary between the water and the air, it's moving from a more optically dense medium into a less optically dense medium where it speeds up. So we know, according to the laws of refraction, that the refracted way is going to bend away from the normal. Here's another ray leaving that same point on my thumb that's traveling in a different direction. It too will bend away from the normal, when it enters the new medium, when it enters the medium where it speeds up. So you'll notice that both of these light rays enter my eye. The problem, as we stated previously, is that your brain is not smart enough to follow the true path that light takes. So your brain thinks that light travels in straight lines. So it is looking for a point of convergence between those two rays. In thinking that light travels only in straight lines, it is going to find a point of convergence where these black lines meet. Notice that point where these black lines intersect is much closer to the surface. So that means that your brain is going to form an image of your thumb, where that point, which is actually quite low in the water, is actually much closer to the surface there. So it thinks your thumb is actually grown. All right. My next magic trick is one for you to figure out. That's what I'm showing you right here. A good magician never reveals his trick. So see if you can figure this one out. Notice we have starting at 2 arrows, a glass full of air. Notice the direction of the arrows. We fill the glass half full with water. Notice how the direction of one of those arrows changes. See if you can use what you've learned from the previous 2 demonstrations to try to figure this one out. How could you use light refraction to explain the change in direction of that arrow, when water has been added to the cup? So in this slide, we'll take a look at a somewhat fun problem involving refraction, and potentially a useful problem that could save your life someday if you were actually, if you found yourself stranded in the middle of the woods where you needed to catch some fish in order to survive. So the problem goes something like this. It says, if you were to catch a fish with a spear, should you aim directly at the fish, above the fish, or below the fish? Well, think about what you know about refraction of light. The light that leaves the fish, and let's take a look at one of these light rays. When that light ray leaving the fish travels through the water and encounters the boundary between the water and the air, you know that because the light wave speeds up, it is then going to travel away from the normal, before entering your eye. So in this case here, where would you actually see the fish? Well, as we've said previously, your brain is not smart enough to follow the true path of light. Your brain does not understand refraction, but rather your brain thinks that light travels in straight lines. So your brain is going to form an image of the fish, in this location. It's going to think that that point on the fish must have traveled, that light must have traveled in a straight line. So it's going to see the fish a little bit closer to the surface than it actually is. So what does that mean? That means that you should actually aim a little bit below, where you perceive the fish to be. So to change this problem up a little bit, what if I were to ask you this question? What if you didn't have a spear but rather had a laser gun? Should you aim above the fish, below the fish, or directly at the fish? Well, hopefully now you realize that a laser gun is really nothing more than a source of light itself. Okay, so the path that the laser light is going to take, okay, because it is light, would follow the same path that the light ray leaving the fish would take upon entering your eye. So in that case, the laser light is going to refract or bend at the surface in exactly the same way as the light ray traveling from the fish is going to bend at the surface before entering your eye. So in this case, you should aim directly at the fish. Okay, there would be no correction needed, okay, when using a laser gun.
So in order to discuss refraction in a quantitative sort of way, where we can predict, okay, quantitatively how much light bends when it enters a new medium, okay, that is to be able to measure an angle of refraction. In order to do that, we need to be able to talk about the speed of light in media. Remember that it's really a measure of how much the speed of light changes when it enters a new medium that determines how much that light is going to bend in the new medium. So rather than dealing with the speed of light itself, we introduce this other quantity called an index of refraction, which we symbolize by n. And light speeds tend to be really big numbers, so we use this concept of an index of refraction to measure light speed as well as optical density. So let's define it here. By definition, the index of refraction of a given medium is simply the speed of light in a vacuum, which we said from Michelson's experiment is about 3 × 10⁸ meters per second, divided by the speed of light in the medium. So you can see here that for media where light travels very slowly, the index of refraction will be bigger. There's an inverse relationship here. For media where light travels very fast, where it travels close to the speed of light in a vacuum, okay, for those cases, the indices of refraction will be very close to 1, okay, when the speed v approaches the speed c in a vacuum. So let me show you a chart here. Here are certain substances and their indices of refraction. So you can see here that certainly for air, light travels almost as fast in air as it does in a vacuum. So you see here that the index of refraction is very close to 1. In fact, it's very often so close to 1, we can just consider it to be 1. You'll see here when light travels through water, okay, it travels slower, so its index of refraction is about 1.33. When it travels through glass, and there's different types of glass, the difference between crown glass and flint glass here. And notice how big the index of refraction is for a diamond here. It's very large. And that has a lot to do with a phenomenon we'll talk about later today, dispersion, that leads to the brilliance and the reason we pay a lot of money for diamonds. So in this next slide, I'm going to put on my magician's hat again and show you one last magic trick involving refraction, really the index of refraction, okay, and light.
All right, this refraction demonstration I think you're really going to like, because you're going to see a little bit of magic right before your very eyes. What I have here is I have this broken beaker that I dropped before coming to class, and I'm going to drop it in this larger beaker here full of vegetable oil here. I'm going to drop it in, okay, and I'm going to get it in there, these pieces, see if I can do it without cutting myself. Okay, this vegetable oil here. And if you want to now focus down here on the beaker, and let's see, we need to do a little magic. How about bippity boppity boo. Let's see what happens here, folks. Okay, notice that, okay, what I am going to do is I am going to pull out that beaker completely intact. Okay, amazing. Okay, no glue necessary, just a little bit of magic. All right, so in this slide, let's see if we can now explain the physics behind the disappearance of the beaker that we saw demonstrated in the previous slide, as well as the reappearance of that brand new beaker from those broken beaker pieces. All right, so let's see, where is our beaker? Hey, not that beaker. Okay, the disappearing beaker. That's the beaker we're talking about. All right, so what's going on here? What is it that made the beaker disappear, okay, in the corn oil when we dropped those broken pieces of beaker in there? Why could you not see them? Remember we said previously that when a wave is traveling from one medium into another, in our case a light wave, that the amount of energy that gets transmitted into the new medium versus the amount of energy that gets reflected back into the medium, okay, depends upon how different the media are. When we say different, what are we talking about? We're really talking about a difference in wave speed. So if a wave traveling from one medium enters a new medium where the speeds are very different, we say that most of the wave's energy gets reflected at the boundary there. But for the case where a wave traveling from one medium into a new medium, the wave speeds are very similar for the two media. Most of that energy gets transmitted into the new medium. Very little of it gets reflected. So when we think about it, we have light which is traveling from the corn oil and hitting the borosilicate glass in the form of the broken beaker. In order for you to see the borosilicate glass, light must get reflected from it back into your eye. But it turns out that the speed of light in borosilicate glass is extremely similar to the speed of light in corn oil. So when the light travels from the corn oil to the glass, almost all of that energy gets transmitted into the glass. Very little of it gets reflected, meaning very little of that light from the glass can get reflected back into your eye, which would make it very, very difficult to see. So you see here, this nicely illustrates the fact that, okay, when light travels from one medium into another, where there is very little change in wave speed, most of that energy gets transmitted, very little of it gets reflected. As to how to explain the reemergence of those broken pieces of glass into a new fully formed beaker, okay, well, that is rather inexplicable. We've got to leave that, okay, to an explanation, okay, lies solely in the realm of pure magic.
So we've said that when a wave travels from one medium into a new medium, that the wave speed changes. What else about the wave changes as it travels from one medium into another? Well, let's take a look. We'll review some of the things we know about wave properties. So if a wave traveling in one medium enters a new medium, let's take a look at these three properties: wave speed, wave frequency, and wavelength. Okay, and we'll ask the question, does the property change as the electromagnetic wave enters a new medium? Well, wave speed, we already talked about that, and the answer is yes. And we said that because when a wave is traveling through a transparent media, that it gets slowed down because the energy has to get absorbed and subsequently re-emitted by the atoms in that media. And this process takes time. So we would expect that the wave speed should change, and the time between the absorption of the energy and the re-emission of the energy, okay, will have everything to do with how fast the wave can actually travel in that medium. So what about wave frequency? Well, The answer here is no. And I'll give you a scenario here. Let's suppose that you were situated at the boundary or the interface between the two media, watching a wave come at you, okay, as it enters the new medium. With nothing better to do, you sit there and you count the number of wave crests that pass you in a given period of time. So what you're really doing is you're measuring the frequency, right? The frequency of a wave is simply the number of wave crests, the number of complete waves that pass you per unit time. So consider what you would conclude if the number of wave crests passing you per unit time were to change. Okay, this would imply that waves were either being created or destroyed at the boundary. Okay, and since waves are a means of transporting energy, okay, then that would imply that energy would be created or destroyed at the boundary as well, in clear violation of the law of conservation of energy. So when a wave enters a new medium, the frequency of that wave does not change. Okay, that would clearly violate this fundamental law in our universe, the law of conservation of energy. So let's think about the implications here. According to the wave equation, okay, if wave speed equals wavelength times frequency, then for a constant frequency, okay, if the wave speed were to change when the wave enters a new medium, then that would imply that the wavelength would also have to change. Okay, so our answer here would be yes. And like we're saying, so from the wave equation, V equals lambda F, okay, if V changes but the frequency does not change, if the frequency is a constant, okay, then the only possibility would be that the wavelength must change as well, okay, in order for this wave equation to remain valid. So, bottom line, when a wave travels from one medium into another, remember that the frequency does not change, but both the wave speed and the wavelength will change in a direct fashion. We can use the wave equation to tell us how the wavelength changes at the boundary in terms of the wave speed. But what we would like to do is derive an expression for the wavelength change at the boundary in terms of the indices of refraction of the two media, the incident and the refractive medium. So let's quickly do that. Let's derive this expression for the new wavelength, I'll say lambda prime, in the new medium, okay, the refracted medium. So let's consider a wave traveling from medium 1 with speed v1 and frequency f1, okay, into medium 2 with speed v2 and frequency f2. So as we said, the frequency does not change. Okay, the frequency of the wave in medium 1 must be identical to the frequency of the wave in medium 2 if the law of conservation of energy is to remain valid. From this, we can apply the wave equation to express the fact that this ratio, wave speed to wavelength in medium 1, must be exactly equal to that ratio of wave speed to wavelength in medium 2. And using our definition of the index of refraction, all right, remember that the index of refraction is the speed of light of the wave in a vacuum divided by the speed of light in the medium. So basically V, the speed of light in a medium, is given by the speed of light in a vacuum divided by the index of refraction for the medium. So we'll just make that substitution for our incident and refracted media. And when we do that and we simplify here, we come up with this expression that n1 lambda 1 is equal to n2 lambda 2, or, okay, written a little bit differently, we can say that lambda 2, that is the wavelength of the wave in the new medium, okay, the transmitted medium, is equal to this ratio of n1 over n2 times lambda 1. So Snell's law is that physical law that gives us a quantitative measure of refraction, telling us how much a wave will actually bend when it enters a new medium. So in this slide, we will actually just state Snell's law. In the next slide, we'll prove it or derive it so you can see where it comes from. So
let's describe here, how are we going to describe the refraction of an electromagnetic wave? Well, some of these terms should be very familiar. So as always, we will define our refraction, just like we did for reflection, as an angle made by an incident and a refracted ray with respect to the normal to the interface, the normal to the boundary between the media. So we have an incident medium, okay, defined by our incident ray. And as we know from last time, okay, some of that wave's energy will get reflected at the boundary between the media. So we talked about in our last video lecture, and some of that wave's energy will get transmitted into the new medium. That's the refracted ray. And N1 will represent the index of refraction of the incident medium. Okay, N2, the index of refraction of the transmitted, or let's say refracted medium. So no surprise here, the angle of incidence, we talked about that before. Okay, the angle that the incident ray makes with respect to the normal. Okay, the angle of reflection, this is just a review, the angle that the reflected ray makes with respect to the normal. And now we can talk about an angle of refraction. Okay, the angle that that transmitted ray, the refracted or bent ray, makes with respect to the normal to the interface. So Snell's law doesn't just apply to electromagnetic waves, it applies to all waves. And remember, we said that the bending of a wave as it enters a new medium is due to the fact that the wave changes speed upon entering that new medium. So this is applicable to all waves, and here's a statement of Snell law that is true for all waves. Okay, whether we're talking about sound waves or light waves, that this ratio of the sine of theta in one medium over the speed of the wave in one medium must be equal to the sine of the angle in our transmitted medium divided by the speed in the transmitted medium. So when we look specifically at electromagnetic waves, remember we said that rather than talking about wave speed, we like to use the index of refraction. So we can make that substitution, okay, and for wave speed in Snell's law. And when we do that, all right, we will end up with this relationship here that, okay, N1 sine theta 1. So if we say that's the incident medium, okay, the index of refraction of the incident medium times the sine of the angle of incidence must be equal to N2, the index of refraction of the refracted or transmitted medium times sine theta 2, that would be the angle of refraction. All right, in this slide we will actually derive Snell's law. Okay, we don't want to just hand wave and state it. We want to show where it comes from. And just like we did for the law of reflection, the law of rectilinear reflection, we said that it can be derived or justified using Fermat's principle of least time. So our derivation here is going to be virtually the same as what we saw for the law of reflection. Let's point out the differences here. Remember, in the law of reflection, we said if we have a light ray which travels from point A, and for the law of reflection, we had point B over here where my laser pointer is, where the cursor is, because point B was in the same medium. And we showed that the angle of incidence had to be equal to the angle of reflection when we minimize the amount of time of travel, okay, between those 2 points. The only difference here is we now make point B in a different medium, okay. If you look at the geometry, that the 2 triangles we're going to look at are identical. The only difference is that now, okay, when the wave enters this new medium, it travels at a different speed than it would in the incident medium. So that is virtually the only difference in our derivation here. So let's quickly go through it. We'll do it quickly this time. So let's consider a light ray starting at point A in medium 1, okay, and ending at point B in medium 2. And we're going to once again start by finding the amount of time it takes for the light to travel this path.
okay, to travel from A to the interface, to the boundary, and then, okay, travel to B in the new medium. And we've got theta 1 and theta 2, right, our incident angle and our refracted angle here. And the time of travel will, just like we did before, be equal to the distance divided by the speed. Okay, the way we get the distance here from A to the interface is just by using Pythagorean theorem. It's exactly the same expression we got when we applied this to the law of reflection. So distance is just the hypotenuse of this side of the right triangle here. Okay, now the speed we will write in terms of the index of refraction, okay, is C over N1 the refractive index of the incident medium, plus the amount of time it takes our light ray to travel from the interface to point B, which is simply this distance right here, which is simply the hypotenuse of this right triangle here. Okay, so we take the square root of the sum of the squares of the legs of that right triangle, and we get our numerator here. And our denominator here, the speed of the wave is now different, unlike in the case of reflection, because our wave is traveling in a different media. Once again, C divided by the refractive index of that media will tell us the wave speed there. So just as before, to find the actual path the light ray travels, we apply Fermat's principle of least time, because remember that the path that light actually takes will be the path that minimizes the amount of time involved. So our variable here, x, which we couldn't express in terms of theta, but our variable x, we need to basically, when we look at the relationship, okay, between the time of travel and this variable x, we want to set that derivative, okay, of time with respect to x equal to 0, in which case we know that when we solve that equation, okay, and find our value for x, that will be the value corresponding to the minimum value of time, right? Because it would represent a maxima or a minimum. So when we take the derivative of this time expression with respect to the variable x and set it equal to 0, this is what we get here. I won't go through all of the the calculations. You can do that. It's very similar to what we did for the case of reflection. Set that equal to 0, and once again you'll notice that the factor of a half and the factor of 2 cancel. We can multiply both sides by c and get rid of that. Once again here the factor, okay, of 1/2 and 2 will cancel here, and the -1 will disappear when we bring that to the other side. And brings us to this point here. And we see here that just like in the case for reflection, this ratio x over the square root of x squared plus a squared, okay, this triangle here, x over the hypotenuse, that ratio of those two sides of the triangle is nothing more than the sine of this angle theta 1. Okay, and likewise, when we take the ratio of L minus x to the square root of this mess over here, the ratio of those two sides of this leg over the hypotenuse, that is simply the sine of this angle here, theta 2. So this simplifies here to Snell's law. We'll finish up our discussion of Snell's law by taking a look at the sample problem, which has a rather interesting result here, and that is, how do you keep CD music noise-free? I think you guys remember what those are, what CDs are. So when we talk about a CD, it is a laser beam that is reading basically pits and grooves that have been etched into a piece of plastic here, all right, on the information layer of the CD. And we're told in this problem the laser beam that reads the information from a compact disc is okay, 0.737 millimeters wide at the point where it strikes the underside of the disc and forms a converging cone with a half angle of 27 degrees, as you see in the figure. So it then travels through a 1.2 millimeter thick layer of transparent plastic with a refractive index of 1.55 before reaching the very thin reflective information layer near the disc top surface. So we're asked in this problem to find the beam diameter, little d, at the information layer. Okay, so how big is the beam here after it has been refracted through this piece of plastic? I think you can see here from the geometry that we're going to have to use Snell's law at some point, and that really this problem is probably more a problem in geometry than it is one in physics. The physics is fairly simple, Snell's law, but there's a little bit of geometry you're going to have to do, a little right triangle trigonometry to be able to arrive at your answer. So let's take a look here. So I'm going to show you here, this is the the laser beam that comes in, and when it hits this, travels from the air into the plastic, okay, you will see that the refraction causes the narrowing of the beam there. So this is quite important, as we'll see at the very end of this problem. All right, so I'm going to get rid of that so we can see our numbers here. And you can see here from the figure that the dimensions of the beam that we're asked to find here, little d, okay, on the information layer, should be equal to, okay, the beam width where it enters the plastic layer here, big D, minus 2 times x. All right, and x here, when we look at the geometry here, using a little bit of right triangle trigonometry, we can say that x is equal to t, the thickness of this piece of plastic, okay, times the tangent of, okay, theta 2 here, really our angle of refraction here. So you'll notice here that theta 1 defines our angle of incidence in the incident media, which is air, and theta 2, which I didn't really fit in here, is our angle of refraction, the angle that the refracted ray makes with respect to the normal. So let's apply Snell's law here to figure out this value for the angle of refraction. Snell's law tells us that, okay, the index of refraction, or incident medium, which is air, times the sine of the angle of incidence, which we're told in the problem is 27 degrees, must equal the refractive index of the transmitted medium, which is plastic, times the sine of the angle of refraction, which we are going to try to find. And when we plug in our numbers here, we find out that theta 2 is equal to the inverse sine of, okay, this expression here, whose values are known. So we look up in the table, we can look up air has an index of refraction, recall, of about 1.0003. We're told the index of refraction of plastic is 1.55. We do the number crunching, and this will give us the value for theta here. So we're going to combine our expressions here. Remember, we're trying to find a little d. So we've got d minus 2x, where x is equal to t tan theta 2. And we will plug in this value here, this expression, all in terms of known quantities for theta 2, for our angle of refraction. And at this point here, okay, we're going to plug in all the numbers and do the calculations, right? So everything is known. We can solve for little d, and we find out that it has a value of about 1.8 micrometers. So it's kind of interesting here to notice that I'm showing you in the figure here the narrowing of this beam, but it is certainly not drawn to scale. All right, notice that at the information layer, that beam is very, very narrow, which it must be in order to read the information. Okay, these pits that have been etched into this piece of plastic here, all right, are quite small. So that means that we need a very small laser beam to be able to read them. Now, you should note here that this thickness is a little bit larger than the pits that are cut into the CD that the information is stored in. This narrowing of the beam plays a crucial role in keeping CD music noise-free. If you think about it, the tiniest speck of dust would blot out information at the micrometer scale, okay, of the information layer. Imagine that if we didn't have the refraction happening, if we didn't have this piece of plastic here that the laser beam had to travel through, if all we had were the pits on this information layer here that had dimensions on the order of micrometers, well, a very, very small piece of dust, okay, would cause so much interference that it would basically mess up the interpretation, the reading of, okay, that sound, okay, sorry, of that wave here. But by allowing a much thicker beam here, okay, at this side of the plastic here, you can see here, which is on the order of 0.737 millimeters, about a millimeter. You can see here that if there's a micrometer piece of dust on this portion of the CD, it is going to be relatively insignificant. It is not going to have any serious effect or cause any serious interference to this beam, which is many orders of magnitude bigger. All right, so and since this side here of the CD, okay, where this plastic exists, represents really the closest distance that dust can get to the information layer. Okay, we see the importance of having that, okay, that 1.2 millimeter thick piece of plastic, okay, to prevent dust from getting at the information layer. That is why we, don't have the laser beam interact directly with the information layer. So it would take, millimeter-sized pieces of dust on this portion of the CD to actually cause you problems. So you see here how this is purposefully built into the design of a CD, right? We can have dust on this surface on the micrometer size, will not cause us any problems because the micrometer size pits at the information layer would require our laser beam to be micrometer sized when it reads the pits, okay? And by the way, I didn't say this, but your CD, which starts out as a flat piece of plastic and has these pits edged into them, gives us a binary reading, right? I mean, either as a pit is interpreted as either a 0 or a 1. So as a laser beam moves along a groove, it's reading, these pits, and where there's a smooth portion, it interprets, let's say, a 0. Where there's a pit, it interprets a 1. And there is this alternating pattern of, flat portion pit, flat portion pit, this binary code, which is basically converted into that electrical signal to produce the sound that you ultimately hear. So we'll now take a look at an effect or phenomenon of refraction known as total internal reflection. If this sounds a little confusing, okay, we will explain why we've got the word reflection in a phenomenon dealing with refraction. Okay, you will soon see. So what is total internal reflection, sometimes written TIR for short? It's a phenomenon where light striking the boundary between two media is 100% reflected from the boundary. So let's take a look at how this can happen, okay, qualitatively at first here. If we have a an incident wave traveling from a medium with a low wave speed into a medium with a higher wave speed, in other words, into a medium where the wave speeds up, okay, then we know that the refracted wave bends away from the normal to the interface. All right, anytime we have a wave going from a more optically dense medium to a less optically dense medium, described by a lower index of refraction, okay, then we know that the refracted ray gets bent away from the normal, as I'm showing you here with the red rays. What would happen, okay, for some incident angle greater than this, we'll say with this yellow ray here, for some incident angle, that refracted ray would be bent so much that it would lie exactly along the interface. In other words, the angle of refraction would be 90 degrees. So we will see later on in this slide that this sets a boundary between refraction and reflection back into the incident medium. So for this particular angle of incidence, this is what we call the critical angle. The angle of refraction is 90 degrees. So you can imagine that for any light ray, okay, traveling from the blue medium into the green medium here, that has an incident angle greater than, okay, the angle I'm showing here, what we call the critical angle. Okay, for any angle of incidence greater than this special case, okay, for the yellow ray, now we would expect that the refraction would be so extreme that the refracted ray would actually lie in the initial or incident medium. And while it really is a phenomenon of refraction that is causing this, okay, it looks like that ray is being reflected at the boundary. So this is why we call it total internal reflection. So, to describe this here, okay, we would say, well, first of all, is it reflection or refraction? Realize that TIR is a phenomenon of refraction. Okay, although it looks like reflection, it is really a phenomenon of refraction. Let's think of it as refraction in the extreme. What are the conditions that lead to TIR? We kind of mentioned it here, but there's really two. First of all, the light ray must travel from a more optically dense medium to a less optically dense medium. Okay, it must travel into a medium with a lower index of refraction so that it speeds up, because as we see, that refracted ray has to bend away from the normal. The total internal reflection could not happen if the reverse were true, if that ray bent towards a normal. And secondly, okay, we would say that TIR happens when that incident angle, that angle of incidence, is greater than some critical angle. Okay, and the critical angle I'm showing you here in this diagram, okay, is the angle made for this yellow incident ray where the refracted ray lies right along, okay, the boundary, right along the interface. So here's the two conditions in which TIR occur, and we can write a quantitative expression for the critical angle using Snell's law. Okay, once again, we define the critical angle to be the angle of incidence where the refracted ray lies along the boundary to the interface, such that the angle of refraction here would be 90 degrees. And when we incorporate that into Snell's law, we can get an expression for the critical angle. So here's our generic expression for Snell's law. Okay, for theta 1, or the angle of incidence, we'll put in theta sub c, the symbol we use for the critical angle. And for theta 2, we said that we have the special angle of refraction of 90 degrees, in which case when we solve this for theta sub c, okay, we get that theta sub c is the inverse sine of this ratio of n2 to n1. Okay, the refractive index in the transmitted medium, okay, to the refractive index in the incident medium. Right, so in this slide we will apply the expression we derive for the critical angle to determine some critical angles for some common interfaces, that is some common boundaries between two media. So we will use Snell's law in conjunction with a table for refractive indices here. And let's start by asking the question, what is the critical angle for water and air? Now remember that total internal reflection is only going to happen, in this case, for an incident ray that starts out in water and travels into air, right? Only from a more optically dense medium to a less optically dense medium. And optical density is measured by the index of refraction. So here, when we use our expression for the critical angle, remember that while this expression is easy, you got to make sure that you get the right value for N2 and N1. Okay, so N2, that is the index of refraction for the transmitted medium, which must be air, okay, for TAR to happen, 1.0003, divided by N1, which is the index of refraction of water. So we see here 48.8, about 49 degrees, is the critical angle for water and air. If we look at glass and air, going through the same calculation here, once again the light ray must be traveling from glass into air. So we've got the index of refraction for air. For glass, there's many different types of glass, but if you're looking at light traveling through a typical window, crown glass would be the more likely candidate for the window. Has an index of refraction of 1.52. Notice that we get a critical angle of about 41.2 degrees. And finally, we'll take a look at diamond air. And you'll see here that because diamond has this very large index of refraction here, when you have a light ray that is traveling from diamond into air, it gives you a very small critical angle. And this is very important when we, as we'll see in our last topic today, we'll talk about dispersion, a phenomenon of refraction as well, and see why people are willing to pay so much money for diamonds. All right, so in the next slide, let's take a look at a demo to see, okay, total internal reflection happen in real time.
All right, folks, I am sitting here in front of this fish tank full of water and a little coffee creamer in it, holding my laser, hoping to demonstrate this phenomenon known as total internal reflection, or just TIR for short. So what is this phenomenon? Okay, well, it's a bit of a misnomer because we call it total internal reflection, but what it really is an extreme case of refraction. Think of it as refraction in the extreme. When a source of light travels from a more optically dense medium into a less optically dense medium, we get light to bend away from the normal. It refracts away from the normal. And this is due to the fact that light speeds up when it enters the new medium. In this case here, I've got a laser, and we'll turn off our light source here. We have a laser beam which is traveling from water, and up here it's hitting air, okay, and when it hits the air it travels through the air. Now in this case here there is no refraction because the laser light is traveling in a direction perpendicular to the interface, in which case the angle of incidence is 0 degrees. Okay, but as that laser beam starts to come in at an angle with respect to the interface, okay, then we see that the light is going to bend away from the normal, as we've already talked about. Now you probably can't see the laser beam in air, but okay, if you take a look at the ceiling, you'll see that the light is indeed coming out of the water surface and is shining there on the ceiling. Okay, it turns out that as we let that angle of incidence get bigger and bigger and bigger, okay, then the bending, the refracted beam bends away from the normal, okay, and it turns out that for some angle of incidence we can get the refraction to be so extreme, that is, we get so much bending that the refracted ray actually bends right back into the initial medium. Okay, the refraction is so extreme it looks like it's being reflected. And that's what you're seeing here. This is a phenomenon of total internal reflection. Really just an extreme case of refraction. And when you look at the ceiling now, you'll see that there is no more light beam coming out. Okay, that the beam that enters the water and hits that water-air interface, that energy is getting completely reflected back into the initial medium, which is the water. TIR, folks.
So an interesting, practical, and very useful application of total internal reflection in modern society is to the technology known as fiber optics. So a fiber optic, used to be called a light pipe, is a long thin fiber, usually made of glass or plastic, with an outer coating that must have a lower index of refraction than the fiber core. And we will see in a later slide how this leads to total internal reflection. I'll show you some examples of fiber optics here in this little slide, the simulation here. And fiber optics, if you look at in the last 25 years, telecommunications have been replacing copper wire with fiber optic cables. And you can see why, really two reasons. One, you can send, as Ms. Prigg is saying here, more than 25,000 conversations simultaneously through a fiber optic that is no thicker than a human hair. So it becomes, in our modern society and our desire to miniaturize everything, it becomes an effective form of communication. The other big advantage of this is that not only does it reduce the amount of space required to transmit signals over long distances, but it increases the energy efficiency as well. So you can send signals through fiber optic cables with virtually no loss of energy. So while you're looking at some examples of fiber optic cables, looking at them really tells you nothing about how they work. But if you think about it, if 25,000 conversations can fit into the diameter of a human hair, looking at a single fiber optic in action won't prove very useful. It's just too damn small. So in the next slide, we're going to take a look at a demonstration fiber optic. I'll say a fiber optic on steroids, one that is actually large enough to see.
All right, so folks, what you see in front of you is a very large demo fiber optic. And you recall, as we were saying, fiber optics make use of the principle of total internal reflection. This idea that if you send light through a medium of high optical density that is surrounded by a medium of lower optical density, in other words, such that the light speeds up as it enters the new medium, that for certain angles of incidence, you can get the refracted ray to be so bent, so refracted, that it actually will appear to be reflected back into the incident medium. And so since the incident medium here is this plastic fiber optic, what that means is that we can get a series of reflections down this fiber optic cable with virtually no transmission of light out the other side. So what you're going to see here is I'm going to take this laser, and when I put this laser light in one side of the fiber optic, rather than traveling in a straight line, you're going to see this laser light follow the path of the fiber optic cable, and you will see it coming out of the other side. Why? Because we have this series of total internal reflections taking place, this extreme refraction that allows the laser light to travel through the fiber optic. All right, so you see how the light will travel all the way down this fiber optic, even when it's bent and twisted, with virtually no loss of energy, because of total internal reflection. What I want to show you now, however, is what would happen if I were to take this plastic fiber optic and stick it in some corn oil, some vegetable oil that has a very similar index of refraction to plastic. In other words, light travels at a very similar speed in plastic as it does in corn oil. Okay, watch what happens when we do that. Okay, so I'm going to stick the bottom of this in the corn oil here. And watch what happens, okay, when we stick this in. Okay, you will notice that up until it enters the corn oil, the light will travel down, but you'll notice that there is no light traveling out the other side. Why is that? Well, it's because in order for total internal reflection to happen, okay, that light that is incident on the boundary between the plastic and the outer surface, either air or corn oil, okay, that angle of incidence must be greater than some critical angle. But it turns out in this case that because light travels at virtually the same speed in plastic as it does in corn oil, the total internal reflection is not possible. Okay, that the critical angle becomes so large that these rays, when they hit that surface, that boundary between plastic and oil, are now leaving. They're getting transmitted rather than reflected. So once again, this nicely illustrates, okay, under what conditions you actually get total internal reflection. Okay, so you must have two media, okay, that have optical densities that are different enough so that light will get totally internal reflected, okay, for very small angles of incidence, okay, which is certainly not the case here.
All right, so let's see what is going on in the fiber optic and how total internal reflection comes into play. So here is the large demo fiber optic I showed you in the previous slide, and it was made of some sort of plastic. And so here you see that the criteria for total internal reflection would be that the light has to travel from a more optically dense medium into a less optically dense medium. So since this fiber optic, this piece of plastic, is surrounded by air, okay, that criterion is met. And if we shine an incident ray here at one end of the fiber optic, if that ray should strike the side, okay, because of the small critical angle here, as long as the angle of incidence here is greater than the critical angle for these two media, we will get total internal reflection occur at this interface. And so then the ray gets reflected, eventually reaches another interface, okay, boundary between the plastic and the air, and if that condition is met, if the angle of incidence is greater than the critical angle, it will experience another total internal reflection. So really what happens here is that you have a series of total internal reflections taking place in this fiber optic that will transport the energy, okay, from one side of it to the other. So this was a demo fiber optic. If you look at a fiber optic that is used in telecommunications technology, it will, well, like the one I showed you, it will be made of glass typically, okay, perhaps plastic, but rather than being surrounded by air, it will be surrounded by this protective cladding here, but one that has a low index of refraction, okay, so that the criterion is still met. And you see here in this simulation that for all those incident rays, okay, they all meet this criteria of having the incident angle greater than the critical angle, in which case, okay, the refracted ray is totally internally reflected, in which case not only do these rays travel down the medium from one side to the other, okay, but there is virtually no energy loss. There is no energy escaping the medium. So it becomes a very efficient means of transporting energy. Here's another simulation. I'll show you this demo, which is pretty cool. You can see that for this laser light, okay, it is also meeting this criteria of total internal reflection, and you can see that, okay, that laser's energy is not leaving, okay, the medium, you know, whatever it happens to be. One more kind of interesting application here that is not much different from the light pipe I showed you in the video clip on the previous slide is the case of a light pipe, which is used in medical diagnostics. So imagine that you've got a problem in your stomach and the doctor needs to look at your stomach. Well, how do you get light down into your stomach so the doctor can see what's going on? Well, these light pipes, think about the large demo fiber optic, the advantage is that that thing can be twisted and turned, and you can see here in the diagram that it's clearly not a straight path from your mouth to your stomach. So you need to put some sort of flexible light pipe down there. And using fiber optics, okay, is pretty much the light pipe like I showed you in the previous slide. Maybe one's a little more flexible. That would probably hurt quite a bit going into your stomach, but you can bend it around your, through your esophagus into your stomach, and not only can you shine light from one end to the other, but you could put a camera down there and communicate what is going on inside of your stomach to the doctor on the other end. So, for all total internal reflection, the criteria must be met that the light travels from a medium with a larger refractive index to one with a smaller refractive index. Okay, and the greater the difference between these indices of refraction, the smaller the critical angle will be, which ensures that more total internal reflection will take place, okay, for the fiber optic. In the next slide, we'll see what happens when this criterion, okay, fails to be met. So in this next slide, we'll see how you can actually make a fiber optic out of a stream of falling water. So this is what I call soda bottle optics, or okay, as you see here in this simulation, you can do this with a laser and a 2-liter soda bottle, okay, letting that water stream fall into a bucket or on the floor if you want. And you'll see that, interestingly enough, it behaves as a fiber optic cable. Okay, you will get the laser light to actually take the path of the water stream. So let's check it out.
All right, folks, what we are going to demonstrate here is the classic Tyndall's experiment. This is a great way to see total internal reflection in action. Remember that we were saying that to get total internal reflection, you have to have light travel from a more optically dense medium into a less optically dense medium. That is, into a medium where it speeds up. And when that is the case, it is possible that for angles of incidence greater than some critical angle, the light will get refracted to such an extreme amount that it is going to appear to be reflected back. And we said that one of the important applications of this is fiber optics, where you can actually get light, and I should say light signals, to get transmitted down some sort of material medium. We said usually a piece of plastic, with basically no energy loss. Why? Because of the repeated total internal reflections at the surface between the fiber optic cable and the boundary, let's say the air. Now, in this case here, we are going to look at another example of a fiber optic. We're going to take a look at how water itself, a stream of water, can actually behave as a fiber optic, in which case we can have total internal reflection take place down that stream of water. And so what you see here, what we have in our setup is we have a tank of water, and I'm going to turn it on in a second. We'll see a stream of water come out. And we have a laser which is aimed right through the stream. Of course, you can't see it yet, but once I turn that water on, you will see that that laser light, okay, is going to follow the stream of water. Okay, it's going to follow the path that the water takes. So let me turn this on and let's see how this works. Okay, and we get our lights here. Okay, and you can see very nicely that you know that laser light travels in a straight line, yet because of total internal reflection, okay, that light is actually following the curved path of the water in the same way light follows a fiber optic cable. Very cool, huh? Okay, cut. Another interesting application of total internal reflection is the formation of mirages. So as you can see here in these simulations, and we'll take a look at the one on the right, the ground heats up, making air in contact with it much hotter than the air that's higher up. This causes the air in contact with the ground to have a lower density than the air higher up. Okay, whereas normally denser air sinks, the high temperature on the ground causes, okay, this inversion layer where the air density actually increases higher up. Light reflected from the sky, as you can see here, gets refracted away from the normal as it travels downward towards the ground. So this illustration kind of nicely shows this. And if you take a look here, you can see these density planes, these layers of air of different densities, okay, increasing air density as you go up. And basically that provides the condition, one of the preconditions for total internal reflection, right? So we get air traveling from a higher density to a lower density so that it gets refracted away from the normal. So as the light travels downwards towards the ground, light from the sun that is, the refraction is so great near the ground that total internal reflection occurs. And here's the thing, since our eye sees light in straight lines, this refracted light, okay, remember our brain is not smart enough to interpret that, so when that light hits your eye, it would see it coming in a straight line. You know, we see it straight ahead on the ground, and this reflected light, which is really skylight, looks, okay, to the naked eye like water. Okay, so it turns out that skylight has the same look. When we actually see the image formed on the ground, it looks like water. Okay, so throughout history, mirages occurring in the desert landscapes, and now we'll revert to the picture on the left. Looks like this camel is experiencing a little bit of a mirage here. Mirages occurring in desert landscapes have led to sightings of all sorts of things. You know, most commonly water and oases, sometimes including palm trees in the middle of the desert. But in modern times, light is behaving quite differently than it ever did in the past, okay, leading to some refraction effects that cannot be easily explained by the ray model of light. So let's take a look at the modern day mirage. See if you can explain that. In the last effective refraction that we'll take a look at today, one that I've alluded to many times throughout this presentation, is what we call dispersion. So dispersion is the property that light of different colors and thus different wavelengths is refracted by different amounts when entering a new medium. So we know that light gets refracted, but it turns out that different colors of light get refracted by different amounts. So you can see that nicely illustrated in this simulation here of the prism, right? That white light actually enters the prism here, okay? But upon really traveling from air into the prism material, okay, some transparent medium like glass or plastic, you'll see that the different colors of light, okay, are refracted by different amounts. So let's try to explain this, try to explain the refraction. Remember we said in a previous slide that there is this inverse relationship between the index of refraction and the wavelength. So as we say here, the definition of the index of refraction, right, C over V, okay, C the speed of light in vacuum, V the speed of light in the material, okay, and according to the wave equation, V equals lambda F. Since F is a constant and C is a constant, you can clearly see here that there's this inverse relationship between the index of refraction and the wavelength of light that enters it. Here's the relationship that we derived on a previous slide, and this tells us too, okay, this inverse relationship. You see here lambda 2 equals 1 over n2. Okay, inverse relationship between, okay, lambda and the index of refraction. So considering this, let's take a look at the relationship between the color of light and the refraction, the amount of bending. Which end of the electromagnetic spectrum would have the largest index of refraction? Okay, the red end or the blue end? Well, okay, using what we know about the chronology of the electromagnetic spectrum and the definition of the index of refraction, the largest n value would correspond to the smallest wavelength. Okay, thus blue light, okay, or violet light, really at one end of the electromagnetic spectrum has the smallest wavelength. Okay, it would have the largest value of n. So, okay, in answering this next question, considering a beam of white light traveling from air into a transparent medium, okay, which color of light should get slowed down more as it enters the new medium? Well, okay, given what we just said, since blue light has a larger index of refraction than red light, okay, that means that blue light should get slowed down more, should have the smaller speed in the new medium, okay, than does red light. And if I then ask which color of light would you expect to get bent or refracted more in traveling from air into the transparent medium, the red or the blue, okay, we would expect that since the blue light gets slowed down more, it also will get refracted more than the red light. And so you see here in the simulation that the white light that enters it, you'll see that the violet or blue light gets bent much more than the red light. As I prefaced in the previous slide, one of the common applications of dispersion is to that of prisms, where we see that the white light that enters one side of the prism is refracted or separated into, okay, its various spectral colors in the electromagnetic spectrum. And this illustration here shows what we looked at on the last slide, but you'll see the white light that enters. You'll see that there's really two refractions that happen, right? So that white light gets refracted at this first interface over here, okay, separating the white light into its various spectrum of colors. You'll see here that the red light gets refracted by a lesser amount than the violet light down here on the bottom, right? Because the index of refraction for red light is smaller than that for blue light or violet light. But also notice here at the second interface, as the light leaves the prism, that it gets refracted a second time here. And that causes further separation of the colors. So one of the ways and some of the problems you get dealing with prisms are really problems of geometry. And we call this angle of deviation here. That is the angle of refraction here that one of the colors, and here they're showing you the angle of deviation for the red light, okay, makes with respect to not the normal to the interface, okay, but that is the angle that the refracted ray makes with respect to the incident ray. So that's really showing you a direct measure of how much, okay, deviation there is, okay, or bending there is due to refraction. Another interesting application of dispersion is the formation of rainbows, where water droplets behave as tiny little prisms to disperse light. So let's take a look and see if we can explain the rainbow formation. What I'm showing you here are two rather large water droplets. The one on the bottom would be a water droplet that's lower in the sky. Okay, the one on top, a water droplet that's higher in the sky. And you see here that, okay, when we have light that enters these droplets from the sun, and that's what I'm showing you here, so at a certain angle the sunlight would enter these droplets. And you'll see here that as the light travels through the water droplet, okay, it gets bent towards the normal, okay, with the initial reflection. You see here that the white light from the sun gets separated into its colors. I'm showing you the red and the purple here at opposite ends of the spectrum. You see here that the red light gets refracted by a lesser amount than the purple light. You'll notice though there's also, when the light hits the back of the droplet, it gets totally internally reflected. Okay, and then it exits out the other side of the droplet. So you'll see here that for water droplets high up in the sky, okay, the refraction, the extreme refraction of that violet light means that when you're standing on the ground, that light will miss your eye. Only the red light, okay, is going to be able to hit your eye. And I've given you some angles here that are described. So only for really that red light leaves the water droplet at a 42-degree angle of deviation from its initial direction, and those droplets can be seen by you on the ground. For the water droplets that are lower in the atmosphere, you'll see the same phenomenon happens here, that the light gets dispersed, okay, upon entering the water droplet, so that we get the separation of colors. But for those lower droplets, the blue light will get, or the violet light will get refracted into your eye, whereas the red light will hit the ground. So you can kind of see here, if I were to ask you the question, what color will you always see at the top of the rainbow, assuming you're standing on the ground, of course. Okay, well, you would expect to see the red light at the top of the rainbow, whereas you would expect to see the violet light at the bottom of the rainbow. So red on top, violet on the bottom, okay, due to the refraction that happens and the separation of colors, which we call dispersion. Right, and the last application of dispersion that I've alluded to a couple times today is, okay, the brilliance that is displayed by diamonds. So what is the physics behind the brilliance of a diamond? Okay, well, let me show you here. When we talk about brilliance, we're really talking about the fact that many colors of light appear reflected off the diamond. And so, you know, the more refraction of those colors of light that enter your eye, okay, the more expensive the diamond. And the cut of the diamond has everything to do with, okay, its brilliance. How much, to what degree you're going to get the separation of colors when the diamond is exposed to white light. So let's see if we can take a look, and these simulations kind of nicely illustrate what's going on. There's really two effects going on here. First of all, as I said previously, because diamond has such a high index of refraction, this means that the critical angle for the diamond-air interface is quite small, which means that total internal reflection will occur for many angles of incidence. So that's the first effect. The second effect is that, since this refracted ray will stay within the diamond for many different trips across the diamond, for many different refractions, because of that small critical angle, it has lots of time for dispersion to occur. Okay, with each reflection, each total internal reflection from one of the faces, this allows more dispersion to happen, more separation of the colors. And separating the many colors of white light into its brilliant spectrum of colors is, okay, what makes diamonds expensive and what you pay for. So the cut of the diamond, and we won't get into that here, but the geometry of the cut can add to this effect, right? Add to the total number of total internal reflections that happen in the diamond and further increase its brilliance, further increase the amount of dispersion taking place.